Hi, welcome to another equipment review video. If you recall from a previous video, we identified that the Siglent SDS5034X was an excellent oscilloscope. The problem identified was with the probes. One of the things I've done since then, I've ordered a new kind of probe. Now what you see on the screen here, the top trace is the original Siglent probe, and if we zoom in, you can see I'm going to call this section here, the spikiness, this hum pattern. I'm going to call it a hum pattern. And you'll notice it's pretty well locked. That's because we're syncing to line. So this phenomenon is from our line voltage. It turns out that our line voltage, because we're running off of a solar inverter, solar inverters are very, very noisy. And that's the coupling, is we're coupling into the scope probes. Okay, the next line down, the yellow line, is scope input with no scope probe attached to show you it's reasonably clean. The next scope probe down, that's the new probe I purchased. And you can see it's got pretty much the same noise level that the Siglent has. And on the bottom, we see the Tektronix probe. Now, it does look like it's a little bit less in amplitude, but I'm thinking that's just because of the configuration of the lead. Because what I did is I went and found that every single lead will pick up this phenomenon, and it's how you have the leads basically arranged. So I went and I took each lead and I kept rearranging it till I could get the maximum signal. So I'm very sure if I played around a little bit further, I could get that signal just as bright as that signal. Okay, now where is this occurring? This coupling is actually occurring this section of the loop here. Let me put it back so you can see. It's this section of the loop here is acting like a loop. And when I put it inside a loop made of its own shield, that's when they pick up the best of that phenomenon the best. So let me show you what I mean. I'm going to point back to the screen. I hear you, kitty. And then what I'm going to do is I'm going to pick the loop up away from its ground, and you can see the problem essentially goes away. Okay, so this problem occurs based on the way the probe lead is coupling to its own shield. Okay, now the thing I found is that it's equally bad in all the probes I have. So there's no benefit, there's no worry over the Siglent probes as far as anything else. What I did find, and let me zoom back out, okay, is the instability of the Siglent probe is an issue. Okay, if I take the Tektronix probe and I wiggle it around, you see that the plot is pretty stable. Okay, I'm going to put it back so it couples to its own shield to pick up the noise. Now I'm going to pick up the new probe I bought. This is a P6500. It is the top trace, the magenta trace. Oh, I'm sorry, it's the green trace. Okay, so you can see when I decouple it from its shield, it gets better. So I can wiggle it around and it doesn't bounce around. The plot trace is very stable. Okay, now I'm going to take the Siglent probe, which is the magenta on the top, and it'll decouple from the noise pretty quickly when I take it up, but watch what happens when I wiggle it around. Okay, that's not acceptable. See the bouncing around of the trace just by moving the cable around? Not good, not good at all. Okay, so the new probe I purchased, this P6500, is $60. Because I looked into purchasing 4 new Tektronix probes and they want $500 a piece. Part of the reason of the cost is that when you have a scope that is 350 megahertz, you have to put 500 megahertz probes on it. Because you don't want the bandwidth of the probe interfering with the bandwidth of the scope. So a 350 megahertz scope, you put on 500 megahertz probes, and those are more expensive than the scope probes you'd buy for a 200 megahertz. For a 200 megahertz scope, you'd buy 300 megahertz probes. Okay, so that's the issue. I'm going to actually be purchasing more of these, and let me put it on the paper so you can see it. These P6500s are $60 a piece, and they're performing as good as the Tektronix probes are. Let me give you a close-up of those. And that's pretty much what it looks like. It's got the compensator here on the end, and it's got the nub, so it interoperates with the scope. That's what I'm looking for. That little nub allows that when you plug it in, that the scope identifies this as a 10 megahertz probe. So that resolves the problem. The one thing I'm wondering now is, does the Regal scope, if you recall, the Regal had a very poor noise performance of its own with no probes put in. I'm beginning to wonder if it's the power, the solar power, its input power is not properly decoupled from the input signals. That's a test I'm going to run next. So that's what we're doing. This is identified the source of the noise. This is very important because when you have a situation where you've got noise from somewhere, you have to identify it so that you can figure out how to eliminate it. And I make sure that if you're going to give data to somebody, you can't get rid of that noise. You have to explain that noise to them, that that's not part of the measurement, that's part of the noise. That's not part of the experiment. Okay, so it's very, 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 very important that any source of noise is identified and understood so that you can either mitigate it or explain it to somebody you're giving data to and say that's just part of the environment. We can't do anything about that. It's not part of the experiment. Okay, a very important thing that has to be done.